Hi students, today we are going to discuss about simple harmonic motion. See, simple harmonic motion is actually a motion which is periodic, right? Now we will see step by step what is a motion, periodic motion, what is a harmonic motion, what is a simple harmonic motion. Then we will derive some equations of simple harmonic motion. Now see here, the simple harmonic motion, see any motion which is periodic, that means which repeats at regular intervals of time is called periodic motion. Okay, see any periodic motion which is according to the sinusoidal law, that means according to sine curve, it is called harmonic motion. See, a periodic motion if it is according to sinusoidal law, that means if the motion is following the sine curve, then it can be said as a harmonic motion. Okay, see, if the harmonic motion is said to be a simple harmonic motion, then the periodic motion, thereby the harmonic motion, is generally caused by the restoring force. If there is some restoring force is there, then only then the force causes the periodic motion. If the restoring force is directly proportional to the displacement of the particle, then it is called simple harmonic motion. It is called simple harmonic motion. Okay, so to take some examples of simple harmonic motion, the best idealized examples are a mass attached to a spring, okay, one of the end of the spring, and other end of the spring is attached to some fixed point, and the whole system is on a frictionless smooth table. And the second one is a simple pendulum. These are the most idealized examples for harmonic motion. So here in this case, while taking the example of a mass connected to a spring, we will derive some equations of simple harmonic motion. Okay, for that just we will consider initially a spring is attached to a mass m. Okay, mass m, this is fixed at this end and other end is attached to a mass m. So when the mass is not moving, that is it is at equilibrium, it is at position O. So when the mass is not moving, it is said to be in equilibrium. So here, depending on the motion of the mass, either to left side or right side, if you stretch the string and if you move the mass to the right side, then the spring will be applying a restoring force on the mass m in the reverse direction, opposite to the movement of the mass. Okay, if you push the mass towards the spring, so the spring will be compressed, so in this direction, then the restoring force will apply on the other side, on the opposite side of the motion of the mass. That is the feature of restoring force, it acts opposite to the displacement of the mass. So this feature can be written by Hooke's law as F is equal to minus kx. So here, if we will take a second diagram, see, to understand better, if the mass is moved from equilibrium position, the mass is moved to equilibrium position, then to the right side, then the spring will be a stretched spring. Okay, So here is the equilibrium position, the mass is stretched towards the right side, then the displacement will be x. Okay, so in this case the movement is to the right side, so the restoring force acted upon by this spring will be towards the left side. So in other case, if the mass is pushed towards the left side, then the spring is compressed. Okay, so the mass will be moving towards the left of the equilibrium position O. So here also the distance we will consider it as x only, the same distance. Here the restoring force will be acting against the push and it will be opposite to the direction of displacement. The direction of displacement is in this direction and the force will be in this direction. So again, while coming to right and left, in between this mass will be positioning at equilibrium position regularly. So it is moving on a frictionless table like this, and at equilibrium position and left position, right position. In this way it will do periodic motion. Here K is the spring constant or elastic constant. So this signifies that the elastic constant is the force required to move the mass by a unit distance, that is called elastic constant. X is the displacement. So here if this is considered, okay, the restoring force will be having some acceleration produced on the body according to the Newton's second law. So this acceleration, in this case it is at equilibrium, it is moved towards right. In this case the acceleration will be in this side, and for this case the acceleration will be in this side. So the restoring force will produce some acceleration. So here if you take the Newton's second law and make it equate with this equation, we can write F is equal to minus kx is equal to ma. That implies ma is equal to minus kx. Okay, so here acceleration can be written as, we know that dx square by dt is equal to minus kx. Okay, so differentiation with respect to time is called acceleration. If this is displacement, if you differentiate the displacement, we will get velocity. If we differentiate again with respect to time, we will get acceleration. Okay, then this is considered as plus kx, okay, is equal to 0. This is again we can write dx square by dt plus k by m, dividing both sides with m, will get is equal to, okay. So here what is, we can consider this k by m as, we know that angular frequency is equal to root of k by m. So with this we can write k by m is equal to omega square here, dx square by dt plus omega square x is equal to 0. So this is the differential equation of Newton's second law. So this is also called the differential form of simple harmonic motion also. So every simple harmonic motion will obey this differential equation. Okay. So here what we have done is, by considering the force as the restoring force and it will generate some acceleration. Okay, so here by applying the Newton's second law, we have derived a differential form of Newton's second law, and this is the, we can call it as the differential equation of simple harmonic motion. Here, how will be the time period of this mass? How will be the time period of this mass? So we know that omega is equal to root of k by m, the angular frequency. So if the angular frequency is omega, what will be the time period? Is equal to 1 by angular frequency. So that means we can write this is m by k, time period of this system of mass attached to a spring on a frictionless table is, can be written as T is equal to root of m by k. So if you look at this formula, this time period is dependent only on the mass and elastic constant or spring constant. So it does not depend on the displacement of the mass. Okay, so it does not depend on x, depends on the spring constant and m. So by this we can say, if the spring constant, the elastic constant is more, because that means the spring is very stiff, then the time period will decrease. So if the stiffness of the spring is increased, it will make a fast oscillations, a quick oscillations, the time period will decrease. Okay, this is about one of the example considering the mass connected to a spring. And now we will go to the next example by considering the simple pendulum, and we will do the derivation for its time period also. Okay. See, what is a simple pendulum? It's an example for simple harmonic motion. We already seen that. See, if you draw a diagram how a simple pendulum will oscillate. See, this is the main position, this is the bob, and this is the string attached to the bob. The string length will be L, and if you consider the extreme position of the bob, so that will oscillate on a periodic regular intervals. So this is the arc in which it will oscillate. So the arc length will be x and the string length will be L. It is at the extreme position, it is making an angle theta with the mean position. So here in the simple pendulum, the restoring force that causes the oscillations will be the gravitational force. That means the weight of the bob, that is mg. Okay, and this restoring force is actually divided into tangential and radial forces components. Okay, this tension is, this tension in the string will make the pendulum to rotate in the arc. Okay, the tension will make the bob rotate in the arc. It is not a straight line motion, it will rotate in the arc. So, and the restoring force, which is a tangential component of the weight, I will show you how it will be. The weight will be acting downwards. So this is the component theta, this is mg cos theta, and this will be mg sin theta. So this is the tangential component mg sin theta will be the restoring force for the simple pendulum to oscillate. Okay. So here the force acting on the bob to cause the oscillation we have discussed as F is equal to minus mg sin theta. In this form we can write. This negative sign indicates the restoring force will be opposite to the, always opposite to the displacement of the pendulum. Okay. See, this displacement, if it is in this direction, So displacement, the restoring force is in this direction, the displacement will be in this direction, so it is quite opposite. So the restoring force will be generating some acceleration. Okay, here in this case, if for small angles of theta, by this equation we can say f is proportional to sin theta, f depends on sin theta also. So if for small angles we can write mg theta, that means for small angles we can write sin theta is equal to theta. So what is theta actually? See here, x arc length, what is arc length? X is equal to L theta, radius of the curvature into angle subtended by this arc at the center of the curvature. So if you put theta in place of x, mg, theta is equal to x by L, right? Theta is equal to x by L. So here, if we know that spring constant, elastic constant is equal to mg by L, right? The spring constant, which is elastic constant, is equal to mg by L. So in this way we can write this equation as f is equal to minus kx. Okay. So we know that the angular frequency is equal to root of k by m. So by this, the frequency of rotation, with this angular frequency, if we consider the frequency of rotation, that frequency can be written as omega by 2 pi. Okay, so this is 1 by 2 pi into root of k by m. So here we know that the k, which is there as mg by L, if we substitute here, we can write the frequency. This is angular frequency, this is linear frequency. 1 by 2 pi root of k, what is k? mg by L. mg by L into m. So m gets cancelled and this will become root of g by L, where L is the length of the string. So in this way, the frequency, if you want to get the time period, what we have to do? We know that time period is equal to 1 by frequency. So that means this becomes, so V is equal to 1 by 2 pi root of g by L. So t is equal to, we know that 1 by frequency, time period is equal to reverse of the frequency. So here the equation will become 2 pi into root of L by g, where L is the length of the pendulum, that is length of the string, and g is acceleration due to gravity. So here we can write finally the time period of simple pendulum is 2 pi into root of L by g. So in this way we can calculate the time period of simple pendulum, and previously we have seen the time period for the spring mass system. So here if you observe, the time period is only dependent on the length of the pendulum, that is length of the string, not on the displacement, not on the mass of the bob, and not on any other things, only dependent on the length of the simple pendulum. If the length is increased, time period will also increase. If the length of the pendulum is decreased, the time period will decrease. So in this way, we can see some of the characteristics, and we can go further into the details of simple harmonic motion. That and all we will see in the next class. Okay.